In this video, I will talk a little bit about the process that we will use to find the magnetic field from current distributions. I'm going to start with the magnetic field equation for a single moving charge. We know that when a source charge Q has a velocity v, at the observation location, you can find the magnetic field that this single moving charge creates by calculating this expression. Now, this is true for a single moving charge. When we have a current carrying wire, we don't have just one, we have a lot of moving charges. And if you take, in very short summary, if you take this expression and you multiply it with the number of charges that you have in a current carrying wire, then this expression will become B is equal to mu naught over 4 pi the conventional current times delta L cross R hat divided by R squared. Okay, this is for a short piece of wire that has a current I, and delta L is just the length, the magnitude of the delta L vector is the length of that short piece of wire, and the direction is the same as the direction of the conventional current. Now, this is what we will use to find the total magnetic field created by current distributions. And I will show you, I will tell you the steps that we will use. The first thing that we need, similarly to finding electric field from charge distributions, you need to write down the vector r obs. This is the position vector of the observation location. We need to know what is the position vector of the source location. Then we need to find r by doing r obs minus r source. And once you find r, we need to find the magnitude. We need to find r hat as the vector r divided by the magnitude. And then we need to know, make sure you know what is the vector delta L. It's a vector, so it needs to have a magnitude and a direction. You need to have the x, y, z components. Then you need to find the cross product delta L cross r hat, because this is what we have in the expression. And then from these we will find the small magnetic field that the short piece of wire creates. I forgot to mention, so even before we start with the r obs and r source, you will have, so let's say this is a wire, and let's say this is a long wire and it has a current flowing through it. We will need to divide the wire into short pieces, and we have to choose an arbitrary piece. So how about I add here step 0, divide in pieces and choose an arbitrary piece. It is important that you choose an arbitrary piece of short wire, and the reasoning is the same as the reasoning I provided in finding electric field from charge distributions. You need to write the vectors for the observation location and the source location in a general way, not for a specific short wire. All right, so we divide in pieces, choose an arbitrary piece, and then for that arbitrary piece we do r obs, r source, the vector r, the magnitude, the unit vector delta L, for that short wire, the cross product, we find the magnetic field that short piece of wire creates. Let's call it delta B sub I from the I piece, from the I short wire. And then step 9, we need to do the sum. We need to add up all the contributions to the magnetic field from all short pieces of wire. And once we have that, we do need to take the limit of this expression from step 9 when delta L goes to 0, or in a different way, when the number of pieces of short wires, when that number goes to infinity. So we need to convert the sum into an integral. And essentially what we're doing is that we're taking the number of pieces and we're saying that n goes to infinity, or equivalently we make the magnitude of delta L to go to 0. Okay, or you can think about doing both at the same time. So this is the process that we need to follow to find magnetic fields from current distributions. And so long as you do everything and you follow the steps, you should be okay. Of course, I forgot to mention, for different current distributions, you may need to use the different coordinate system. Express your position vectors in terms of r, theta, or s, theta, phi, and so on.